Hi, everyone. My name's Teagan. I'm a PhD student here at Monash, and I'm going to be talking about some work that I've been doing with Max Easy over in New York and my supervisors, Paul and Eric, all about black hole ring downs. Okay, so here is a binary black hole merger. And the part that I really want you to focus on here is right at the end, once they've merged together and it's still kind of bouncing up and down, that is the ring down. And once they merge and it's doing the ring down, it's still emitting gravitational waves, but in kind of a different way than the rest of the binary merger, as I'll show you. So this is the gravitational waves from that binary black hole, now presented as gravitational wave strain in the time domain. And so what you can see here is the in spiral as the black holes are coming together, the merger, which is a highly energetic nonlinear regime where they're merging together. And then finally, once they're merged, this ring down region here. And what's really interesting about this is that the ring down lets the black holes transition into a linearly perturbed black hole. And so what that means is that in like general relativity, we're able to predict what the frequencies and damping times of these ring down tones are going to be. And so what this means is that we have this ring down signal, we have this prediction for a whole bunch, an infinite number of overtones that make up the signal. And then what people try to do is they try to measure these tones and see if whether or not they match up with the predictions from general relativity. And what this lets you do is test the no-hair theorem for black holes and general relativity. So it all seems simple enough, but what if I told you that these few wiggles are the basis for dozens and dozens of papers? And so what's going on? This is something that I've started to call the overtone tension. It's like the Hubble tension, except it's just way more intense and way more controversial. So what's going on here? On one side, you have this idea that the overtones of the binary black hole ring down are physically there and easy to measure. And in fact, what groups on kind of this side of the divide say is that you can apply this linearly perturbed black hole ring down model all the way to the merger. So sort of, before we might expect that it would actually be linear. And not only that, but you can measure 7 overtones at this peak time of the merger. And what that also means is that we can actually see an overtone already in the gravitational wave 150914. So that first binary black hole, they've presented a overtone detection for that event. All very exciting. However, then we move over to this other side where they say, nope, overfitting these overtones is overfitting. It's not physical at early times, so you can't do it all the way to the peak. And they're really hard to measure because if you wait till late times, all of your signal to noise ratio is gone. And so what do they say? We need to wait till late times in this signal. And so you can really only fit at best maybe 1 overtone before you can't measure anymore. And we absolutely cannot see an overtone in 150914, and any claims of doing so are simply overfitting, and you shouldn't listen to them. So what's going on? This is where we come in to try to figure this out. And what we have tried to do is make a self-consistent model for measuring the ring down tones. And so what I mean by that, first we get our ring down data, and then we measure tones by measuring their amplitudes at different times in the data and then seeing whether or not they are actually consistent with each other as they go on. And to do that, we needed a criterion for saying whether or not they're actually consistent. And then finally, we use Bayesian inference to get our uncertainties on all of these measurements. Okay, so what is the data here? The data that we use here is a numerical relativity waveform from the Simulating Extreme Spacetimes collaboration. And what it really is solutions to Einstein's field equations. And it's the most accurate simulations for gravitational wave data that we have. And so, yeah. So next we thought about what it would mean for these tones to be self-consistent. And the framework that we decide was that we say that we want our tones to match up at least at the 95% credible interval level at all start times that we measure. But then some of them will eventually become consistent with zero, and then that tone's unresolved, like it's not stable or unstable. And so that's what I'm kind of trying to show in this plot. So this is the amplitude and phase of the fundamental tone for this waveform. And the teal is showing what we get when we only measure with one tone. And so you can kind of see that these posteriors in the violin plot are moving. They aren't like constant with each subsequent tone until sort of here at about 40 m. By the way, we use geometric units, so time are measured in m, don't think about it. Okay. But then when we go to a 5-tone model, which is the orange, you can see that these amplitudes and phases kind of level out and they're approximately the same value at each time step. And that means that we are calling this tone stable. Okay. And then finally, what do we actually do to measure these tones? So we use Bayesian inference to measure the amplitude and phase of each tone. We fix their frequencies and damping times to their GR predictions. But of course, you could also try to measure those as well in your model. Using Bayesian inference to measure the tones hasn't actually been done before with the numerical relativity data. So that is new. And then finally, we use a Gaussian likelihood and we set white noise and we use the MC sampler. And so a lot of the choices we make around the likelihood and noise and all of that are phenomenological. So not necessarily motivated in physical reality, but you know, when you're trying to use these samplers and sort of measure something like this, you have to make choices. And so that's what we did. You can feel free to ask me more about that later. And so what do we actually get? So what I am showing here are the first 4 overtones of our data and posteriors for their amplitudes. And so this is just kind of one like snapshot of the posteriors for one time step, but keep in mind we do it for a bunch of time steps and then see how closely the amplitudes match up each time. And what we do when we find that the 220, the fundamental tone, is stable at all times, which is like that plot I showed with the orange posteriors. Great. Okay, we can at least, you know, measure some sine Gaussian tones to the data. 221, stable at some times. So this one starts off unstable, becomes stable for a little while, and then becomes unresolved. Okay. The 222, which is the next highest tone with the next longest damping time, is stable at some times, but you know, not stable compared to the previous two, and then becomes consistent with zero. And then finally, we measure the 223 tone, which has a shorter damping time again than all the previous ones, and it's unstable at all times before you can't see it. And so that is where we stop, because with the inclusion of these tones, we get a relatively self-consistent picture. And once we get to an unstable tone, we stop, and any subsequent tones are also unstable and also don't really improve the fit. Okay. And if you like log likelihoods, this is what we get when we plot the log likelihood for each of our models. So with the dark blue is like the smallest number of tones added, just the fundamental 220, and then gradually increasing them till our highest amount of tones with the orange here. And so luckily adding tones does improve the likelihood, which suggests that the fit does get better. The improvement is pretty minimal after about 30M, which suggests that after that point, all of the other tones have damped away and you just have the fundamental tone. And the other thing you can kind of see is that as you add the tones, the improvement to the likelihood kind of becomes smaller each time until you get to the orange, and it's like almost a straight line with just this little little increased slope bit here. And so what we think that means is that by the time you're at the 223, once you've got 4 tones in your model, you've pretty much included all of the tones that are resolvable, at least in our framework, except for like some amount of potential like non-linearities and extra stuff that's going on here. Cool. So this schematic shows kind of the main conclusions, which is that you have the literature which is very sort of like divided, and then you have us in the middle and what we say. And so what we find is that we fit up to 5 tones self-consistently, but additional tones result in instabilities and higher tones just being consistent with 0 with this Bayesian modeling procedure. Thank you. Pretty much done anyway. But sorry. Anyway, but we can't say for sure whether they are actually physical or still a phenomenological like fit. But it's actually unclear how to decide this. And so if you want to know more, you can check out our paper. Now I'm done.
Very interesting work. So I have a question related to how you choose the amplitudes and phases of the output. So see there are 3 different degrees of freedom. So the number of tones you want to capture, then what amplitudes they have, and then what phases they have, and then you sum them up as exponentially decaying sinusoids, and then see how well that compares to the fusion of the rotation wave in the ringdown phase.
Yes.
So how do you choose the amplitudes and phases?
Yeah, so what we do is we test each number of tones like separately in its own model, and then we sample in the amplitudes and phases, and we just choose a uniform prior for the samplers for both of those.
Okay, so
and then we fit them. Yeah, so you get these like posterior histograms here, or I actually have extra slides that might help with this. Yeah, so each of these violins is like running MC like again, and sampling in the amplitude at that time.
So you first talk about phase, and then you try to find the reason amplitude.
No, so we fit both at the same time. So then I don't know if I have. So like this, for example, this plot, which is overwhelming, which is why I didn't include it in the main talk, but this is everything, the posterior of everything that we measured at once in one model. So you have a violin for the amplitude, the phase of for 2 tones, because that was what this particular model was for. And then we also fit a frequency in this model. And so that's also included. And so each violin is essentially like the entire posterior distribution for that parameter, for that fit. Does that make sense?
Yeah, just that you need to repeat the exercise for every binary. So characterized by total mass of the binary.
Correct. Yes.
That I guess goes for just one.
Yes. Yep. So we were using a sort of a 1509-14 like numerical relativity simulation.
Maybe. Cool. So
Yeah.
Ilya, quick question, then set up, and then Alex, quick question.
Quick question. What units are you measuring the amplitudes in? Because I was surprised to see that the amplitude for the fundamental mode is actually much lower than the amplitudes for some of your higher harmonics.
Yeah, it's a really interesting thing. So everything's just in the like geometric units. And yeah, what happens is the I don't know what was I gonna say. Oh yeah, so what kind of happens is because the tones have really short damping times and they decay away, they tend to get really high amplitudes. Oh, and I should say that we quote all of our amplitudes and phases as being at the peak, even when we don't actually measure at whoop, should I stop sharing?
And I'll take this.
Yeah. Yeah, so when we like make these plots of our posteriors, they're all quoted for the peak time, even when we don't actually do the measurement at that time, just so that it makes it easier to compare.